Hello everyone, welcome back to CompilerSutra. Today we are going to discuss about 6th stage of the compiler. We know that this software word, or also referred as virtual word, everything here is written in one of the programming language. It can be any language, but we also know that we need we also know that the hardware only understand the binary. We people write code in a language known as high level language, but hardware only understand code written in binaries. Then how this conversion happen? There should be some tool which do that. In this tutorial we are going to discuss about the 6 stages of the compiler, but before going into that topic I would discuss something very important to you, that is how the toolchain basically work. So we write code in a high level language or a human which we can understand, but hardware only understand the binary. So there must be some tool which is used to translate this high level language to the binaries. This tool is known as not compiler. It's known as tool chain. So basically whenever we write any source code, let me show you the flow which I have already discussed in my previous video, but when I will discuss here in much detail, you should be at the same page. Whenever we write any source code, this source code is given input to a tool chain, and this tool chain generate what? Binaries. This tool chain will generate what? This tool chain will generate what? Binaries. So basically how this tool chain work? This tool chain consists of 4 important components. First is preprocessor, second is compiler, third is assembler, and then linker, and then loader. These are the complete 4 stages of a tool chain. This is the complete stages of the tool chain. But now the question arises, why we all needed these 4 or the steps? That I already discussed in my previous video, whose link I have provided in the description. You can go and watch it. So now let's dig deeper a little bit. Here SC stand for not supreme code. It simply means source code. We will open this compiler as a black box. Currently we are treating compiler as a black box, and we will see what compilers do and its 6 stages in this video. So whatever I am going to discuss with you in this video, it will be mostly from this tutorial which I have already published on my website, which you can go and watch. In order to watch that, you can go into the web page CompilerSutra. There you will find a compiler navbar. Then you can click on that. When you will click on it, it will load, and here you can see from inside the compiler what things are there. I am going to discuss about this. This link I will provide in the description after this video will end. You can basically go and read about it also, in order if you want some notes and other things for the things which I am going to discuss with you in this today's video. So now let us first discuss what compiler is. Everybody from the school or colleges, people know that compiler is a machine which translates, but they only say that people mostly define compiler wrong way. What they say mostly, compiler is a tool which convert high level language to low level language. That is partially correct, not completely correct. So what basically compiler is? Compiler is a tool which convert one language to another form. This is the more appropriate definition of it. So basically when we are talking here about system design or in the domain where we have to interact with the system program, then when we talk about compilers, then mostly compiler take the pre-processed out input as a .i file and generate what? A assembly file. This is the role of compiler. What is the role of compiler? Compiler take pre-processed input file and generate what? Assembly language. This is the role of compiler. How does compiler do that? We will discuss in this video. So basically, currently for everyone who are here, compiler is what? Compiler is a black box. We will try to open it. And we also see practically how each stages are connected. So when I talk about compiler, see, this is a compiler. It is taking pre-processed input and generating what? Generating what? Assembly language. Now, if we want to open this black box, then the modern compiler such as or a framework such as LLVM, how they have architecture, we can see as in this format. There will be three things. First is front end, then middle end, then back end. Now let's understand each role. This front end role is to take .i file and understand the language syntax and gives us the error, syntax error whenever there is error, and generate a intermediate representation which is equivalent to our source code. Then this IR is given to the middle end. This middle end, what does it do? It run target independent optimization and generate one optimized IR. Generate one what? Optimized IR. This optimized IR is given to the back end, and this back end run here target dependent optimization and generate one machine intermediate representation, and from there we get a assembly. This is the complete flow. Now we will see how each one interact with each other. So basically, we have seen compiler to be divided into three parts: front end, middle end, and back end. We will see how each part work together. So basically, when I say front end, its role is to take what? Its role is to take our source code or the pre-processed file and generate one intermediate representation. How does front end do that? It happened in 3 stages. What does 3 stages are? There are lexical analysis, then syntax analysis, then semantic analysis. Once these 3 parts is done, we get a middle end. In the middle end, what is the input? The input will be the IR, and we get what? Optimized IR. Here mostly in the target independent optimization works. When I say target independent optimization, what does it mean? That our optimization has nothing to do with the hardware. They are mostly generic and it will work for all the hardware. So here optimization such as dead code elimination, constant propagation, loop fusion, all these things works together. So this optimized IR is given to the backend, and backend run the hardware related optimization which is required for that particular hardware, and this is then it generate one MIR, and once we get the MIR, then from there we get a assembly. This we have understood. Now let's see in more detail how this structure works. So basically, I will top to down I will draw. This is our pre-processed file which we are taking as input. Once we have taken that input, then what? Then front end of the compiler will come. So in that front end, or this front end is also called as synthesis phase, and back end is and middle end are called as analysis phase. See, front end job is to do 2 things. First one is to generate IR which is semantically equivalent to the .i file, and also second is to give us error and generate a symbol table. What this symbol table is, whatever value I am getting, I will put in one data structures which is important for us. So this is called a symbol table where all the symbols of the code are kept. So now these are the 2 work of the front end. How this front end do all this work? Let's see. This front end first our source code, the front end read as a line by line or a character by character. So front end read our source code character by character, and there is a one again tool or lexical analysis which run on it, and it generate what? Stream of token. What does it mean by stream of tokens is that, let us suppose I have a code int a equals to 4. So here int is a keyword, a is a variable, equal to is a operator, 4 is a again a variable, 4 is a constant, and semicolon is what? Semicolon is or termination condition end, that here the code will stop. This is the complete line. So when we write like this, int a equal to 4, it simply means what? It will convert into a token. Let's see how compiler do that. In compilers such as clang, there is a command if you want to see the token, that is called as clang dump tokens. Let's see how it works. So basically, let us suppose we have a code as where I want to calculate the area of a square. So for that purpose, I have defined pi equal to 3.14, then I define area pi r cross r, then int main, int radius equal to 5, and then is my screen is showing you black or how it is? Is my screen is black currently, or you are able to see? Oh, okay, you are able to see. I think now. Yeah. So basically here, if you see, we have a code where we want to see stages in compiler. Here I have defined macros as defined pi 3.14, and then we are calculating the area, and area of a circle. Area of circle is what? Pi r square. So for that purpose I have created here pi r into r. So I have defined a variable as 5, then I have called a function in the form of macros, and then here area, and we are passing a parameter as radius, and when they are printing it. So this is the simple code where we want to calculate the area of, right? So now let us see how compiler look into it. Whenever I write using any compiler clang -v, or see, basically whenever I want to see the area, let us suppose I write see, basically see so I have ran the command, this command, and here I have used the flag as xclang dump token to dump the token, and I have stored them in a token.txt. Let's see what token.txt consists of. So these are the lexemes of the token which compiler generate in the after the lexical analysis end. So here in our source code, basically if you see, here what we here is a semicolon, then int is int as identifier. Let me here if you see all our source code related things, which is like int is a what? Int is a keyword. So compiler has noted down, hey, this is the location at line number 6, and it is a keyword, and main is what? Identifier. So it has taken the location, the compiler, and saying that means the if you see your code as here, see from int main, it has not done anything with the preprocessor. Why? The compiler will take input from the preprocessor. So if you want to see what all the things, let us suppose when I have a see, I have stages in a compiler. If I want to compile with a, let us suppose if I want to see what is the pre-processed input we get from the, which is we give input to the compiler, we see that the compiler take input as let me show you. So here I have used a -e flag with the clang, and when I have used the -e flag with the clang, it is generated the preprocess.i. When we open this preprocess.i file, then here you see that the whatever macros I have written earlier in my code has defined other thing has been removed, and their values has been replaced here. So this type of things is done in macros. So we have seen, right, how the tokens are dumped. Once token got dumped, once we have dumped the token, then from that tokens we check whether the syntax is correct or not. Then a syntax analysis run on it, and it generate what? It will generate a syntax tree. Syntax tree will be a tree-like structure where all the data type which we have stored in the form of a token, we have gathered the information. It will create tree-like structure for it. So from there, parsing actually start. So once the syntax tree is generated, then there will be again a semantic checking will be there, and then we get a IR. So this is the complete flow of a front end. So how the front end basically move from the front end from the front end there is a lexical analysis phase. So from the front end lexical analysis comes and we get what? Stream of token. Then from there syntax analysis, from syntax analysis we get what? Syntax tree. From syntax tree we get a semantic analysis comes. Then from semantic analysis we get generate one IR. This is the complete flow of the front end. So at the front end we got what? One IR. Let's see what is the flag if you want to see IR by itself. How you can see the IR? So now let's see how we can see the IR. Here don't worry, see here I have one make file and stages in compiler. Make file is just a build tool. So let us suppose if I want to build anything, build means compile plus link, then I use make rules for that purpose. So if you forget any command or if you want to use any, write anything, so make rule will be very beneficial for that purpose. So see, this make file is consist of very simple things. What compiler I am using, then which source code I am using, then what all the how which flags I am using to build my tool chain or the compiler or the particular input for the particular input what I am using. So what rule I want to pass. So I have just written some simple make rule, so which is really easy for me to show you what things I want. So instead of doing that, so if in order to see the what front end is, we can just write make clang. Sorry, we will use make rule there. Make IR. So if you see when I write make IR, then compiler run this command, or basically what I want to invoke is clang hyphen sysroot, then hyphen s emit LL stages and then IR. Just forget upon hyphen high sysroot. I will explain in some other videos what does it mean by hyphen sysroot. Now let's see if I went to ir.ll how this file look like. If you see we have defined macros and we have include the floating point, and then what we have did, we have just multiplied 2 into 2, and you understand what we have did in code, you understand, right? Let me again show you the code. What is the code will look like? See, basically pi 3.14 pi I cross I radius 5. So we are defining radius 5, then we are calling area function, which is defined in the form of macros, and then we are printing the area. So similarly, if you see here in IR, it's printing the variable 11. What is variable 11 have? It is to what is stored in 10. What is stored in 10? 10 is PTR2, right? It's loading from the value PTR2. So this is the way how the IR will look like, which is semantically equivalent to your what? Source code. So this is what the actually front end generate, and here all the compiler related stuff or middle end and back end basically work. So now we understood, right, what is the front end work is. Front end work is simple. Front end work is to generate a IR, which is semantically equivalent, and also it shows throw the errors in the sense of what, or let us suppose if we are getting any syntax error, let me modify something in the code. Let us first understand by syntax and semantic error. So here if you check, if I remove semicolon from here, the compiler should throw error, right? What error? Hey, we accept at the end of declaration. This is called a syntax error. Now you just think of, just let me make radius as 5.5. Radius is 5.5 and we want to store, we are storing it in an integer, which is logically incorrect, because 5.5 is what? Decimal value. Decimal value should be stored in float or double, depending upon how much precision you want. But we are storing in an integer. It's a logically incorrect statement, but syntactically equivalent. Syntactically it is correct, but semantically it is wrong. So here, when we write int, the radius will be deprecated to int value, and instead of 5.5, it will become 5. So even though if I will calculate the area, it will give me wrong output. See here, warning it is giving that implicit conversion of double to int, which is because why? Because it is semantically not correct, even though it's syntactically correct. So semantically means, let us suppose if you are dividing any number a by b, so b should not be equal to 0. That is mathematical definition, because we can't divide any number by 0. So all these things, even though they are syntactically correct, but their logics are not correct. So this will call as semantically incorrect code. Even though if you see, the binary will get generated with some warning, and I will try to compile, and it will make me 78.5 value it will be generating, which is incorrect. So here it should be basically, if you want to make 5.5, I have to make here float. Now again I will generate it. See, now area value has changed, because that I will cover in later videos why this has happened, but just keep in mind that the syntax and semantic analysis, they are both are different. Now we have understand the front end. Now let's understand the back end and middle end. So basically we have understood that the front end of the compiler take what? Pre-processed file and generate what? The front end will take what? .i file take .i file and generate what? Intermediate representation. So this intermediate representation is given to what? Middle end. And it will generate what? Optimized IR. Now let's see how it look like, IR, optimized IR. So basically for that purpose, we will use the different flag to see the different optimization flag compiler have, to see all the optimization compiler is running. So here, if I am using compiler as Clang, so what will happen? See, here is one flag which Clang provide in order to see all the optimization which Clang is going through. So that is called as, that optimization, that flag is -m print after all, and -o2 means the optimization I want. So here it will dump all the on a terminal. So in order to redirect into output file, we can write as out.ll. So let's open out.ll and how it will look like. So here we have open out.ll. So you will see this is our IR which is given input to the compiler. Now what compiler is doing on each IR, what it is doing, it is modifying the IR and checking where the modification is correct or not. Two things middle end is doing, what? Modifying the IR and checking whether the modification is correct or not, and is dumping IR dump after every pass which is running on it, and that passes are known as see here, this is the how it will look like. So here what is that, every this is how the IR look like. But now middle end is doing two things. What? It is running everything Screen is still coming black. Okay, now it's fine. So now this is what how IR intermediate representation, which the IR which I initially show you, it look like a how it will look like a intermediate representation which is given by the front end. Now the middle end has taken that as input and has run multiple passes. Everything will now work on IR. So two things will happen in IR. What IR will get modified, or IR will, once modification will be done, then IR will be rechecked whether modification is correct or not. So you will see here IR dump after IR dump after IR dump after IR dump after IR dump after. So when you see, right, there are total 221 instances. So 221 passes are running in to optimize your particular pass. So you can see how much internal things compiler goes through. So whenever you see such things, such as if you see here dead code is not there because there is no such loop is not there also. So let me say constant, maybe have constant propagation may have run on it, constant, or better way is you can just if you want to see how what all optimization has run, just you can just grep for the, so it will show you what all optimization compiler has run. So if you see this middle end, see all type of optimization has been run over it. Instruction combine, vector combine pass. So some are machine dependent. Here mostly if you see all type of optimization machine has did. But what I told you, machine, this middle end work is to generate one optimized IR which is passed to the back end. So this conversion happens after instruction selection. So if you will just see here the pass, just see how the things has been different. After this, see IR dump after shift stack instrument pass after dump. So after that you will see now the something like assembly will show you, like copy SP means a stack pointer, which is now you see the intermediate function has defined no undef I2 30 min. Still you are unable to know which function it is and where it is not. But after this instruction selection, what you see, there is a calling to something different, or you are seeing machine instruction like move I64 IAM, which is more close to the assembly language and it is dependent on machine. This move I64 IAM may not be in every target. It will be only present in ARC64 because I am running on a ARC64 machine. If you are running on different machine, it will show on different machine. And when you keep on it, you will see this type of optimization. So this is where backend start working. Backend work is to, once optimized IR is generated, make it more friendly for the particular hardware and generate the assembly code. So if you want to see, so we have understood, right, what first compiler generate the front end. Compiler is divided into three parts: front end, middle and back end. And the front end role is to generate the IR, middle end role is to optimize the IR, and then back end role is to take the optimized IR. Once the optimized IR is taken, then from that generate what to then generate machine IR and then assembly. This is the complete flow. And we have also seen in the IR how it look like. So this your code. Now just see, if you want to just see how the assembly will look like. So for that purpose, the compiler has one flag which will directly show you how the assembly will look like. So it has generated stages in compiler. Let's see how it will look like. So here if you see, right, this is how the assemblies look like, what the compiler will generate. So this is the role of backend to generate it, but backend generated by how? By taking the IR from the middle end. So and how this complete flow is, then we first of all this whatever code we will have, it will be written in some form of character. So we call it as a character stream. So character stream is given to lexical analysis, which take in a form of token, which will give output a token. And how to see token? For that purpose, token you can write that clang -m and then generate it and see it, how it will look like. So basically this is the complete flow. Now let's once I will revise it and then I will end my session. So basically our source code is given to compiler front end, where first come lexical analysis which generate what? Stream of tokens, which is again given to syntax analysis which generate syntax tree, which is given to which will given to the semantic analysis, which will generate what? A IR. These three together called as front end. Front end role is to generate first IR, second symbol table. We will know about symbol table more in our upcoming lectures, which you can subscribe my channel till that time. And third IR, symbol table, and the third is it will also give us error. Let us suppose if you are writing a code which is have some mistakes and your compiler is not able to give the error, then that compiler is not useful. That is just a stupid box. Because once you know the error, then you can fix it. If you don't know the error, then you can't fix it. And this IR from here the interesting thing happens, where I have worked a lot in the optimization part. So there will be this IR will be generated. Some people call it intermediate code generation, or not intermediate. Mostly people call it intermediate representation only. So now this intermediate representation will be given on that multiple optimization run, depending upon what type of code you have written. If you have not written a code which will logically not call it called optimization, that optimization won't run. So here mostly what we can say, target independent optimization runs. What kind of optimization? Target independent optimization run on it. And target independent optimization we run on it, and we get what? Optimized IR. And then this part is called as middle end, whose goal is to produce the IR which is more optimized, and optimized in the sense of what? Optimized in the sense of what? Size and see, optimization basically, if I talk about if you have written or read on your book, there are two types of optimization which mostly people talk about: space and time. But in today's era, there is one more type of optimization which is power. So mostly power optimization will be. This is one question for you: where will the power optimization will be? It will be in middle end or back end? You people can answer me in comment or later once you have got those answered. So now middle end, right? Once we have middle end, this optimized IR, this where is become this. Is given to this optimized IR is given to backend, and this backend work is to generate what? MIR and assembly. So this is the complete workflow of this compiler. 1, 2, 3, 4, 5, 6 stages, where compiler work is. So basically Here in MIR, most of the hard related optimization we do. This is the complete stages. Now let's see how we will see each. Let us suppose if you want to debug particular stage, if you want to see whether token are generated or not, then here you will use a flag called as dump tokens. Here for this purpose you will use dump tokens. To see the AST you will use AST dump. To see the IR you will use -emit LLVM. To see all the optimization passes MLLVM print after all. So let's see each one by one. So what I told you, if you want to see the token generated by the compiler, then what we will use? First of all, let me clear you one thing. See here, I have I have a two folder. I have folder compiler. In that, two files are there. One is make file and one is stages in compiler. This make file is just simply, I want to keep my all command in one place. I don't want to mess up, so I have created it. You just, if you want to know more about what make file is, you can just Google about what build system is and understand why they are used. This is not the scope of today's tutorial to discuss what make file is. I will discuss with the commands which we have. So when I write make help, so here I have created make all. Forget about this. So just say if you want to see the token, if you write make tokens, then the compiler is, the tool chain is executing the command as -xclang dump token f syntax only. So when you use this flag, you are able to see the tokens, and this tokens is getting redirected into this file vimtokens.txt. When I open this vimtoken.txt, you will see int is created token for the int at the line number 6. Then it identify a function as main, then length parenthesis, then right parenthesis. So whatever we have given here, all the spaces and comment will be removed here, and all the spaces and comment will be removed, and whatever you will see here, they are mostly without any space, and all the comment has been removed. So the lexical analyzer take all the source code in the form of character by character, means one character at a time. Let's say when I say A, B, C, D, so it will take A, then B, then C, then D. So here int is 3 word, so it will take int as a one keyword, then it will go for main, MAIN, then it will match where it works. So that's why it works how the character by character way. So similarly you can see for other thing. Now what I second stage is to see how the syntax analysis work. So for that purpose, what I have told you, there it will create one abstract syntax tree. So let's see how it will look like. So here let's write for AST. So you can use this flag -xclang AST dump. What it will generate? It will dump one AST. Right? How it will look like? Let's see. Here it's, see how it is showing you int 128 and a constant string. See, this is how the AST look like, and here where your code is. These are the include file which I have included. They also get included in your source code by the preprocessor, and they all get included. So that also compiler parse. So now if you see, there are function, whenever it's a tree-like structure, function inside function, there is a compound statement, there is a declarative statement, there is a variable, there is an implicit cast expression. So here, if you see how your code look like, this is how the abstract syntax tree look like. That's not the scope of today's tutorial to explain you, just to show you how it look like. We will see in later lectures how to understand it. Now the third part is, this is the where front end work end. It will generate the errors. If no errors, it will put the things in the symbol table, and also it gives two things, symbol tables and intermediate representation. So let's see the flag for intermediate representation. When I write make, so for that purpose I will use this flag -emit LLVM. So I already show you how the IR will look like. This is the way how IR will look like. And now in order to debug middle end and back end. The LLVM toolchain provide middle end. To debug middle end we use OPT, and to debug back end we use LLC. And for everything for the LLVM we take IR as an input, not any source code, because you have seen, right, front end role is to just generate the IR. Once IR is generated, then front end role finish there, and that IR is passed through middle end and back end. So this is the way how each workflow. So that's all from my today's video, and if anyone have any question they can ask, or else I can end the video.